Black holes represent a truly enigmatic presence within our universe, existing as entities that defy full explanation even by the laws of physics as we currently understand them. Anything that dares to venture too close, including light itself, is destined to be swallowed. These celestial titans are born from the dramatic collapse of massive stars, possessing a level of power and complexity that reaches far beyond the boundaries of our contemporary scientific knowledge. What truly lies within a black hole? Is it a realm of infinite, empty nothingness, or perhaps a gateway to an extraordinary dimension? From their immense gravitational pull to the theoretical domains of wormholes and quantum secrets, black holes offer us a fleeting glimpse into the exhilarating unknown. Today, we will unravel the science and the many conjectures surrounding these objects, peeling away the layers of what is known to face the mysteries that remain unsolved. It is a long story, so let us begin this journey as if entering a dream, and before we start, remember to engage with our community. The event horizon is a boundary where the known laws of physics are pushed to their absolute limits. It encircles every black hole and is often referred to as the point of no return because once an object crosses this invisible line, escape becomes impossible. To understand this, we look at escape velocity, which is the minimum speed required for an object to break free from the gravitational pull of another body. On Earth, for instance, a rocket must reach at least 11 kilometers per second to escape into space. However, as the mass and density of a celestial body increase, so does its gravity and the required escape velocity. In the case of a black hole, the gravity is so intense that the escape velocity exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing can escape the event horizon. It is important to realize that the event horizon is not a physical surface. It lacks a solid shell like a planet or a star and is instead a theoretical boundary. If you were hovering just outside it, you might not even realize you were at the edge of the most extreme phenomenon in the cosmos. Yet, once you cross it, escape is a physical impossibility. This is not due to a visible barrier, but because the curvature of space-time caused by the black hole's immense gravity is so extreme that every possible path within the horizon leads directly to the center. From one perspective, the event horizon is the defining threshold of a black hole, for without it, we would be unable to distinguish these objects from other dense celestial bodies. From another perspective, it serves as a shroud that conceals the interior. At the center of the black hole lies the singularity, a point where space-time curvature becomes infinite, hidden by the event horizon so that no information from this internal region can ever reach the outside world. This means scientists cannot directly observe or study the singularity. Because of this veil of mystery, the event horizon stands as a tantalizing border between the observable and the unknowable. From a distance, an external observer would see an object approaching the event horizon appear to slow down. This effect, known as gravitational time dilation, arises because the black hole's intense gravity literally stretches time. To the distant observer, the falling object seems to freeze at the edge, growing dimmer and redder as its light is shifted toward the red end of the spectrum until it eventually vanishes from sight. However, for the object itself, time appears to pass normally, and it would cross the event horizon in an instant without feeling any immediate change at the boundary itself. The size of the event horizon is determined by the mass of the black hole it surrounds. Stellar mass black holes, formed by the collapse of massive stars, might have event horizons spanning only a few kilometers, while supermassive black holes at the centers of galaxies can have horizons reaching millions or even billions of kilometers. When matter, such as gas or dust, approaches the event horizon, it is drawn in by gravity, often forming a swirling accretion disk. As this matter spirals inward, it is heated to extreme temperatures and emits intense radiation, making the area around a black hole one of the brightest places in the universe. Yet, once that matter crosses the horizon, it vanishes from our view forever, contributing its mass to the black hole. According to quantum mechanics, information regarding the state of particles should never be lost, yet anything falling into a black hole seems to disappear entirely once it crosses the threshold. This apparent loss of information challenges the most fundamental principles of physics and is known as the black hole information paradox, a puzzle that remains one of the greatest unsolved problems in theoretical physics. The Schwarzschild radius represents the distance from the singularity to the event horizon, named after the physicist Karl Schwarzschild who first derived this solution. This radius is the key to understanding the geometry of space-time around a black hole. At the Schwarzschild radius, the curvature of space-time reaches a critical point where the escape velocity equals the speed of light. This implies that within this distance, neither matter nor energy can find a trajectory leading outward, all paths inevitably curve inward toward the singularity. Imagine space-time as a stretched rubber sheet. A black hole is like a heavy weight placed in the center, creating a deep and steep well. The event horizon marks the edge of this well, where the slope becomes so steep that nothing can climb back out. Within this radius, the very fabric of space-time is so distorted that all directions point downhill toward the center. Outside the event horizon, the black hole's gravity still warps space-time, but with enough energy, an object can still orbit or even escape. However, as you approach the Schwarzschild radius, the curvature becomes increasingly extreme, and space and time begin to behave in counterintuitive ways. To a distant observer, time slows down for the falling object, while space appears to be infinitely stretched toward the black hole. Crossing the Schwarzschild radius signifies a fundamental transformation where the flow of space-time is so distorted that the roles of time and space effectively swap. Outside the horizon, you have the freedom to move in any direction in space forward, backward, left, or right. Inside, however, the direction of time becomes aligned with the path toward the singularity. Just as we cannot stop moving toward the future in our daily lives, once you enter the Schwarzschild radius, you cannot stop moving toward the singularity. It is an irreversible, one-way journey. The physical conditions near the Schwarzschild radius are extreme. As matter approaches the event horizon, it is subjected to tidal forces caused by the gravitational gradient, meaning the difference in gravity over a certain distance. In smaller black holes, the curvature changes more sharply, making these tidal forces incredibly violent. In contrast, for much larger black holes, the tidal forces at the event horizon are relatively weak, potentially allowing an object to cross the Schwarzschild radius intact, though the subsequent journey toward the singularity will eventually become destructive. Outside the event horizon, particles and light still interact with the intense gravitational field, resulting in phenomena like gravitational lensing, where the light from distant stars is bent, distorted, or magnified. Close to the Schwarzschild radius, this bending is so strong that light can actually be forced into a circular orbit around the black hole. This region is known as the photon sphere, and it sits just outside the event horizon, marking another strange boundary in space. At the deepest heart of the black hole lies the singularity, the place where conventional physical laws break down in the face of immense gravity. While the event horizon marks the boundary of no return, the singularity is the true core where all infalling matter is compressed into an infinitely tiny point. When a massive star reaches the end of its life, its core is crushed to a state where no known force can balance the pull of gravity. The collapse continues until the entire mass of the star is squeezed into a volume of zero size, where density and space-time curvature become infinite. General relativity fails to provide clear answers under such extreme conditions. In most of the universe, we can use classical physics or relativity to describe the behavior of matter and energy, but at the singularity, these rules lose their meaning. The concept of infinite density is incompatible with our understanding of the natural world, suggesting a realm where space-time itself ceases to function. Outside the black hole, gravity acts as a force pulling objects toward the center, growing stronger the closer one gets. At the singularity, however, it is no longer just a force, it is the absolute end of space-time. Scientists believe that to truly understand the singularity, we need a new theory that unifies general relativity with quantum mechanics, often called quantum gravity. Perhaps in a quantum gravitational description, the infinitely small point is replaced by a region where matter is compressed to its smallest possible state, governed by quantum laws. Until such a theory is established, the singularity remains one of the greatest mysteries in physics. Equations from general relativity also hint that singularities might appear in other contexts, such as the Big Bang. Before the universe began to expand, the early universe may have been a singularity of infinite density and curvature. If this is true, studying black hole singularities could provide vital clues about the origin of our universe. Unlike the event horizon, which can be observed indirectly through its effects on light and matter, the singularity is hidden and cannot be seen. Anything crossing the horizon is irreversibly dragged toward it, but what happens there remains a subject of intense debate. Does the matter become part of the singularity, increasing its mass, or does it undergo a transformation we have yet to understand? These questions touch upon the fundamental nature of matter, energy, and space-time. The existence of singularities also suggests that our current understanding of physics is incomplete. Some scientists argue that a singularity is not a physical entity but a mathematical warning sign indicating that we need a deeper theory. Others believe the singularity is real, marking the frontier where new physics will eventually be discovered. As matter gradually approaches a black hole, it enters a region where the gravity that feels gentle and uniform on Earth becomes a relentless, magnifying force. The closer matter gets, the greater the difference in gravitational pull between one point and another, creating what we call tidal forces. Imagine a long object, such as a spacecraft or even a human body, falling feet first toward a black hole. The gravity is not uniform, the feet, being closer to the center, experience a much stronger pull than the head. This difference in gravitational strength stretches the object along its length, with the lower part being pulled down much harder than the top. The result is that the object is gradually elongated and thinned out. Simultaneously, a horizontal compression occurs. While being stretched vertically, the object is squeezed from the sides. Gravity acts from all directions, and near a black hole, the geometry of space-time means that lateral forces push inward. This combination of vertical stretching and horizontal squeezing pulls the object into a long, thin shape, a process vividly described as spaghettification. For smaller black holes, these tidal forces become extreme even before the object reaches the event horizon. Near a stellar mass black hole, a person or a ship would likely be torn into molecular or even subatomic fragments before ever reaching the boundary. In contrast, for supermassive black holes with masses millions or billions of times that of our Sun, the event horizon is much larger and the gravitational gradient is gentler. Theoretically, an object could cross the horizon of a supermassive black hole relatively intact, initially feeling almost no stretching at all. However, As it continues to move inward, the tidal forces rapidly intensify, making spaghettification inevitable. Regardless of the black hole's size, the ultimate conclusion is the same. This applies to gas clouds as well. Particles that once traveled together are pulled apart, forming a long, thin stream that spirals toward the center along distorted space-time orbits. Even solid bodies like asteroids or stars cannot withstand these massive tidal forces. As a star approaches, its outer layers are stripped away first, creating a spiraling flow of gas. While the core might briefly hold itself together through its own gravity, it is eventually shredded, and its remnants are stretched and compressed, releasing massive amounts of energy that heat the surrounding gas and produce intense radiation. This is why the area around a black hole is often among the brightest in the cosmos, even though the black hole itself is invisible. From the perspective of someone falling in, spaghettification would be a disorienting experience. The distortion of time would make intervals feel strange, and as the body is stretched, the perception of space and distance would be warped. The singularity ahead might appear both infinitely distant and yet right in front of you. Eventually, even the structure of atoms is destroyed, reducing everything to fundamental particles. This is not mere speculation but the true language of black hole physics. The Schwarzschild black hole is the simplest member of the black hole family. It does not rotate and carries no electric charge. It is often viewed as the starting point for understanding black holes because it strips away all extra complexities, leaving only mass and gravity. Unlike rotating black holes that drag space-time with them, the Schwarzschild black hole is perfectly symmetrical. Its hallmark feature is the event horizon, whose size is determined solely by the black hole's mass. A black hole with the mass of our Sun would have a Schwarzschild radius of about 3 kilometers, while the entire Earth, if compressed into a black hole, would have a radius of less than 1 centimeter. This clear relationship between mass and size makes the Schwarzschild black hole an ideal model for theoretical physics, allowing us to study the foundations of space-time and gravity under the most extreme conditions. Another core concept is the no-hair theorem, which suggests that a black hole is entirely defined by only three observable properties: mass, charge, and spin. Since a Schwarzschild black hole has no charge or spin, it is defined by mass alone. This simplicity makes it a fundamental paradigm for testing new ideas in relativity. In a real astronomical environment, these black holes are often surrounded by accretion disks of gas and dust. While the black hole itself emits no light, the infalling matter is heated and radiates strongly, allowing us to see its presence indirectly. Theoretically, a Schwarzschild black hole could also be paired with a hypothetical white hole, an object that behaves as the opposite of a black hole, ejecting matter rather than swallowing it. Together, they could form what is known as a Schwarzschild wormhole or an Einstein-Rosen bridge. Kerr black holes differ significantly because they rotate, and often quite rapidly. This rotation introduces new phenomena, most notably the dragging of surrounding space-time in an effect known as frame dragging. Imagine placing a heavy ball on a rubber sheet and spinning it. The sheet would be twisted and spiraled around the ball. Kerr black holes do exactly this to the fabric of reality. This frame dragging creates a unique region called the ergosphere, located just outside the event horizon. The ergosphere is shaped like an oblate spheroid, flattened at the poles and bulging at the equator. Within this region, space-time is dragged so forcefully that it is physically impossible for any object to remain stationary relative to the distant stars. Even light is forced to twist along with the rotating space-time. Unlike the event horizon, the ergosphere allows for a fascinating possibility: energy extraction. The physicist Roger Penrose proposed that a particle entering the ergosphere could split into two, one part falls into the black hole while the other escapes with more energy than it originally had. Thus, the rotational energy of a Kerr black hole could theoretically be harnessed. Furthermore, the singularity of a Kerr black hole is not a point, but a ring. This ring's singularity is a result of the rotation stretching the central point into a circular shape. Located inside the event horizon, its unique geometry opens up theoretical possibilities for travel to other regions of space-time or even other universes. While extreme gravity and quantum effects likely make such a journey impossible in reality, the idea remains a profound subject of study. In Kerr black holes, accretion disks tend to align with the black hole's spin, and frame dragging pulls the inner edge of the disk closer to the horizon, allowing matter to reach higher speeds and temperatures. This makes them the engines for some of the most powerful phenomena in the universe, such as relativistic jets. Near the poles, charged particles are accelerated to near the speed of light by magnetic fields and rotational energy, creating high-energy beams that can extend for thousands of light-years. Falling into a Kerr black hole would be even stranger than a Schwarzschild one, as the frame dragging would twist your trajectory into a spiral rather than a straight line toward the center. Finally, we consider charged black holes, which carry an electric charge in addition to their mass. While the stars and gas that form black holes are generally electrically neutral, extreme conditions could theoretically result in a charge imbalance. The presence of an electric charge profoundly alters the space-time structure. Unlike the simple single horizon of a Schwarzschild black hole, a charged black hole can have two horizons, an outer event horizon and an inner Cauchy horizon. The outer one remains the boundary of no return, while the inner one arises from a delicate balance between gravitational and electromagnetic interactions. In the absence of charge, the singularity is a point of infinite density, but in a charged black hole, the repulsion generated by the charge competes with gravity, changing how matter behaves as it approaches the center. This competition doesn't stop the black hole from forming, but it creates complex dynamics in the interior. Charged black holes also feature regions of effective gravitational repulsion, where the combination of charge and gravity makes the force point outward in certain areas. This causes charged particles to follow complex, spiraling paths rather than falling straight in. Although charge represents another reservoir of extractable energy, charged black holes are likely rare in nature because a black hole with a significant charge would quickly attract particles of the opposite charge and become neutralized. For any hypothetical traveler, the electromagnetic forces near the event horizon would significantly alter their motion and the observable characteristics of the surrounding radiation. Black hole-like objects represent a class of compact celestial bodies that appear remarkably similar to black holes. They are capable of trapping or significantly delaying light and generating intense gravitational effects, yet they lack the one defining feature of a true black hole, the singularity. Because they do not possess a core of infinite density or extreme space-time distortion, these objects are not genuine black holes, but rather profound mimics that use their immense mass to imitate certain gravitational characteristics. When an object becomes sufficiently dense under its own gravity, its surface gravity strengthens dramatically. If the density reaches a specific threshold, the escape velocity can approach or even exceed the speed of light, which is the hallmark of a black hole. However, black hole-like objects often stop just short of this critical threshold, where light might be temporarily trapped or delayed in its escape, creating the illusion of a shadow around them. A classic example is the neutron star, the remnant of a massive star following a supernova collapse. Its nuclear density is staggering, such that a small amount of neutron star material would weigh billions of tons on Earth. This intense gravity can significantly bend light rays, sometimes even curving light from the far side of the star toward the observer, allowing one to see almost the entire surface at once. While this gravitational lensing is similar to what occurs around a black hole, a neutron star has a solid surface and therefore no true event horizon. Other theoretical candidates include gravastas, which propose that just before a collapsing star can form a singularity, quantum effects or dark energy-like properties intervene, creating a strange state of matter. This results in an object without infinite density, leaving instead an ultra-dense shell that approximates an event horizon. Although no definitive evidence exists, these objects remain a major focus of theoretical research. Additionally, there are families of ultra-compact stars, such as hypothetical quark stars or boson stars, which are even denser than neutron stars and may exhibit more black hole-like behaviors, such as the formation of a photon sphere, significant time dilation, or high-energy jets, driven by powerful magnetic fields. The key difference remains that these mimics lack a true point of no return. Instead of an absolute boundary, they possess physical surfaces or additional interaction layers where infalling matter would eventually collide and release bursts of X-rays or gamma rays, a stark contrast to the way matter simply vanishes when crossing into a real black hole. Time behaves in extraordinary ways near a black hole, and the experience of actually falling into one is even more surreal. To a distant observer, as you approach the event horizon, all your movements and signals would appear to slow down. In their eyes, you would seem to freeze at the edge, never truly crossing the boundary. However, for you, time continues normally, your watch ticks, and your heart beats just as it always has. Near the horizon, the curvature of space-time is so extreme that light-carrying information struggles to escape the gravitational pit. As light climbs out, it loses energy and shifts toward the red end of the spectrum, its wavelength being stretched. To the outside world, your signals become slower and dimmer until time itself appears to stop. But for you, within your own local frame of reference, gravity feels constant and time flows forward, even as the world around you becomes increasingly distorted. Once you cross the event horizon, you effectively disappear from the perspective of the external universe. As any light or signal is trapped and cannot return. For you, however, the crossing is not marked by a physical barrier, there is no obvious sign at the moment of entry. Within the horizon, space-time is so warped that every possible path leads toward the central singularity. Your future is literally written into the geometry of space. Regardless of your efforts, your destiny lies at the core. As you get closer to the singularity, the distortion becomes more violent and tidal forces strengthen. A smaller black hole would tear you apart before you even reached the horizon, whereas in a supermassive black hole, the tidal forces are weaker at the boundary, potentially allowing you to venture deeper before feeling the destruction. Deeper still, the very nature of time changes, becoming so twisted that the concepts of before and after become difficult to distinguish. If you could look back at the external universe, you would see time speeding up in a fast-forward motion, stars would age rapidly, galaxies would evolve, and the entire cosmos would seem to race toward its end. Inside the horizon, the distinctions between past, present, and future begin to dissolve. At the singularity, the laws of general relativity no longer apply. Some theories suggest the singularity might connect to other parts of our universe or even to different universes entirely, while others propose that quantum effects prevent a true singularity from forming, replacing it with a more complex structure. Imagine an astronaut working near a black hole. To them, everything feels routine, yet to a distant observer, their actions look like they are in slow motion. Even the light signals they send are stretched and delayed, a phenomenon known as gravitational redshift. The closer one gets to the horizon, the more difficult it is for signals to escape and be detected. This illusion of freezing means that for those outside, objects falling toward the horizon seem to stay on the edge forever, when in reality they have already crossed over and are heading toward the center. The event horizon is a one-way door not just for matter, but for information as well. This extreme time dilation makes a black hole, in a sense, a natural time machine. Orbiting a supermassive black hole for just a few hours could mean that years or even decades have passed on a distant ship when you return. This is a one-way trip to the future. You can travel forward, but there is no turning back to the past. In principle, we could imagine using a black hole's gravity to leap into the far future, but the reality of intense radiation, tidal forces, and the immense energy required to escape the vicinity makes such a journey nearly impossible. Even if successful, returning to a world that has moved on so far would bring profound philosophical and temporal dilemmas. Outside the horizon, a black hole acts like a frozen photograph of history, while inside, time continues its march toward the singularity. This duality is one of the most counterintuitive charms of relativity. After passing through the event horizon of a rotating Kerr black hole, you would not head straight for the center as you would in a non-rotating one. Instead, you would encounter another boundary deeper within, the inner Cauchy horizon. This structure is unique to rotating black holes and marks the point where the predictability of space-time breaks down. Beyond this point, the principle of general relativity that a given present can predict the future fails. One cause of this unpredictability is the accumulation of energy and information near the Cauchy horizon. Matter and radiation falling into the black hole are squeezed by the rotational gravity and pile up in this region, becoming blue-shifted and heated to extreme levels, sometimes referred to as a blue sheet of radiation. Theoretically, this environment could be violent enough to destroy anything attempting to pass through, making survival unlikely. However, some models suggest that if the black hole has absorbed very little matter, this accumulation might be weak enough to allow a brief window for passage. What lies beyond is even more mysterious. In a Kerr black hole, the singularity is shaped like a ring, which might be accompanied by even stranger space-time structures. Some theories even imagine it as a passage to other regions of space or different universes. The problem is that these ideas are highly idealized and lack direct observational evidence, with much of our understanding coming from mathematical models and simulations. Yet, it is at the Cauchy horizon that the predictions of general relativity begin to fail, highlighting our need for a theory of quantum gravity to describe what truly happens there. Some research suggests the energy buildup is enough to trigger a collapse of the internal structure, while other views hold that under certain conditions, the internal geometry might remain stable. One of the most bizarre concepts in black hole physics is that once inside the event horizon, space and time effectively swap roles. Our familiar universe is a four-dimensional space-time consisting of 3 dimensions of space and 1 of time. Gravity warps this fabric near mass, and while this warping is gentle outside a black hole, it becomes extreme near the horizon. Once you cross over, the equations of general relativity show that the radial coordinate becomes time-like in its mathematical nature, while the time coordinate behaves more like space. This does not mean that space and time literally trade places, but rather that their roles in the equations of motion are reversed. Outside the horizon, you can choose to move inward or outward in space, while time only moves forward. Inside, the radial direction moving toward the center becomes an irreversible direction in time. You cannot move against the flow of time. And therefore you cannot move outward to escape. The singularity is no longer just a point in space, it becomes your future in time. This blurs the lines of causality. If the direction of time is locked toward the singularity, then cause and effect within the horizon follow rules entirely different from our daily experience. Some speculate that in the early universe, space-time might have undergone a similar role reversal on a grander scale. Black holes force us to re-examine the most basic structures of reality. At the singularity, physics is not simply the end of a classical path, instead, quantum effects are dramatically magnified. Quantum fluctuations are tiny, omnipresent energy ripples in the vacuum of space-time, born from the uncertainty principle which prevents us from knowing a particle's position and momentum simultaneously. While these fluctuations are usually too small to notice, they are amplified near the extreme curvature of a black hole. In a quantum framework, the singularity might not be a definite point but rather a fuzzy region of intense fluctuations where microscopic structures are born and destroyed in an instant, potentially preventing true infinity from ever occurring. Various quantum gravity theories, such as loop quantum gravity, propose that space-time is made of tiny, discrete fundamental units, like the fibers of a fabric. If so, the singularity would be a complex interaction of these units under extreme conditions. In such an environment, effects like quantum entanglement might dominate, and novel particles or fields could be created, disrupting the conventional flow of time. While we lack direct observations, scientists are looking for indirect ways to test these ideas, such as analyzing the gravitational waves produced by black hole mergers to see how space-time behaves under these conditions. Einstein-Rosen bridges, or wormholes, are solutions to the equations of general relativity that act as tunnels connecting distant regions of space-time or even different universes. Mathematically, the bottom of a black hole's pit could extend into a passage, with the other end appearing as another black hole or a theoretical white hole. A common analogy is to think of the universe as a sheet of paper. By folding it and punching a hole through 2 points, you create a shortcut rather than traveling across the surface. This suggests that wormholes could enable faster than light travel or even time travel. However, the practical challenges are immense. General relativity shows that wormholes are highly unstable and would collapse instantly. To keep them open long enough for passage, one would need exotic matter with negative energy density to provide outward pressure, a substance that has not been found in large quantities in nature. Even if such matter existed, the tidal forces at the entrance might be stronger than those of a black hole, destroying anything that tried to enter. Despite this, various wormhole models have been proposed, from the simple Schwarzschild wormhole to more complex ones derived from rotating Kerr black holes, which theoretically offer a better hope for stability but still rely on exotic matter. Some scholars even imagine that quantum wormholes might exist at the smallest scales as part of the space-time foam. If a wormhole were to be traversable, it would have to overcome its own gravitational collapse. Theoretical models show that the throat of the wormhole tends to close immediately. Holding it open would require exotic matter to push outward against gravity. While phenomena with negative energy do occur in the quantum vacuum, they are too minuscule to stabilize a cosmic-sized wormhole. Even if exotic matter were available, its distribution would need to be incredibly precise. Furthermore, the tidal forces near the throat could still be lethal, requiring advanced geometric design or protection. In the 1980s, physicists like Kip Thorne proposed models for large traversable wormholes, showing they aren't strictly forbidden by the laws of physics, but they remain purely theoretical for now. Additionally, if the two ends of a wormhole are in different gravitational potentials or moving at different speeds, it could lead to time travel and its associated paradoxes. Stephen Hawking proposed the chronology protection conjecture, suggesting that nature would spontaneously prevent such paradoxes from forming. Nevertheless, the existence of traversable wormholes would revolutionize our exploration of the universe, allowing instant travel to galaxies billions of light-years away. In a Kerr black hole, the rotation pulls the point-like singularity into a ring. This ring's singularity, formed by the angular momentum of a collapsing star, creates a region where space-time behavior is truly anomalous. A tantalizing idea is that the center of this ring might not be a solid core that crushes everything, but rather a void through which one could pass to other locations. Unlike the dead-end singularity of a Schwarzschild black hole, the geometry of a Kerr ring might allow for trajectories that bypass the most destructive zones, depending on whether a stable path exists. However, real black holes are unlikely to be perfectly symmetrical, and infalling matter would likely disturb this delicate internal structure, potentially closing any windows of passage. Whether the ring's singularity truly exists or is replaced by something else is a question only quantum gravity can answer. If the universe contains more than the 4 dimensions we know, black holes might serve as natural gateways to higher dimensional realities. Some imagine black holes as cosmic recycling centers, taking matter and energy from one region and expelling it elsewhere, perhaps even as the origin of our own universe via a white hole in a parent cosmos. These ideas remain speculative but are deeply rooted in mathematical exploration. White holes are the time reversal of black holes. While nothing can enter them, they constantly eject matter and energy. Some have speculated that gamma-ray bursts might be related to white holes, and some even view the Big Bang as a kind of white hole event. However, white holes face significant challenges, including extreme instability. Even a tiny amount of matter falling toward them could trigger a collapse into a black hole. Usually, a singularity is hidden behind an event horizon, a concept known as the cosmic censorship hypothesis, which suggests that nature hides the chaos of the singularity from the rest of the universe. Yet, some solutions to Einstein's equation suggest that under extreme rotation or charge, an event horizon might not form, leaving a naked singularity exposed. Observing such an object would provide a unique laboratory for studying nature at infinite density. While no evidence for naked singularities exists yet, future simulations and observations may provide more clarity. Entropy measures the number of ways a system's microscopic states can be arranged. If you throw high-entropy matter into a black hole, it seems to disappear, which would violate the laws of thermodynamics. Jacob Bekenstein proposed that black holes themselves have entropy, proportional to the area of their event horizon rather than their volume. Stephen Hawking then discovered that black holes are not completely black, they emit radiation and thus have a temperature. This link between entropy and surface area sharpened the information paradox. What happens to the information that falls in? If it is lost, it violates quantum mechanics. If it is preserved, how is it retrieved? This led to the holographic principle, which suggests that all the information in a 3-dimensional volume can be encoded on its 2-dimensional boundary. Some believe the information is encoded in the subtle correlations of Hawking radiation, while others suggest it is scrambled at the horizon but not lost. In 2012, the firewall hypothesis was proposed, suggesting that instead of a smooth crossing, an infalling observer would be instantly incinerated by a wall of high-energy particles at the horizon. This remains one of the most debated topics in theoretical physics, as it forces a choice between the smooth space-time of general relativity and the information conservation of quantum mechanics. Finally, quantum tunneling allows particles to pass through barriers that would be impossible to cross classically. Hawking radiation itself can be viewed as a tunneling process. While escaping from inside the horizon classically requires exceeding the speed of light, quantum tunneling offers a probabilistic way for information to leak out, eventually leading to the complete evaporation of the black hole over trillions of years, leaving behind only quantum remnants in a universe governed by discrete, Planck-scale structures. When gravitational collapse reaches its ultimate limit, quantum effects may generate a repulsive pressure that halts the process of infinite compression. In this framework, the traditional, problematic singularity is replaced by a finite, computable, and ultra-dense core known as a Planck star. These objects remain hidden deep within the event horizon, emitting no light or heat, but they effectively swap the concept of infinite density for a structured, finite reality. Consequently, the process of black hole evaporation may differ significantly from classical expectations, as this core might exchange energy and information with the external world through as yet unknown quantum processes, eventually leaving behind a quantum remnant that preserves the information once thought lost. The event horizon of a black hole appears capable of storing a staggering amount of information proportional to its surface area. If we view this boundary as a holographic screen of quantum bits, the black hole functions as a natural quantum information processor. Any information drawn into it is encoded, rearranged, and computed by quantum states on the horizon before being eventually output in the form of Hawking radiation. While this remains a theoretical proposition, given that the extreme environment near the horizon makes direct manipulation nearly impossible, it has inspired bold new pathways in physics where space-time is equated with entanglement and geometry is viewed as a form of computation. This shift encourages us to use the language of quantum information to finally decode the mysteries of gravity. Some theories further suggest that a black hole is not an endpoint, but a beginning. As infalling matter reaches the quantum limit of density, it may undergo a dramatic rebound, carving out an independent bubble of space-time and igniting a new Big Bang within the interior. In this view, every black hole could potentially birth a daughter universe, inheriting its physical constants and laws from the parent black hole's characteristics. If this is true, the multiverse may be governed by a form of natural selection, where universes that more easily form black holes reproduce more frequently, eventually dominating the cosmic family tree. Our own universe's suitability for creating stars and black holes might simply be the result of this immense evolutionary pressure over countless generations of cosmic birth. While dark matter neither emits nor absorbs light and is known only through its gravitational influence, it is fundamentally different from a black hole. However, some scientists propose that primordial black holes, formed directly from density fluctuations in the very early universe, could account for the gravitational effects attributed to dark matter. While observations such as gravitational microlensing have placed limits on certain mass ranges, suggesting primordial black holes may only contribute to a portion of the dark matter, the relationship remains a subject of intense study. Dark matter can be pulled by a black hole into a dense spike at the center of a galaxy, potentially enhancing radiation signals or altering the black hole's growth history. Even if they are not the same entity, black holes and dark matter appear to be engaged in a long-term cosmic dance, where dark matter influences the formation of the stars and holes that ultimately shape the evolution of entire galaxies. The accelerating expansion of the universe is currently attributed to dark energy, but some bold researchers have hypothesized that the extreme quantum vacuum effects of black holes could be related to vacuum energy itself, perhaps even contributing to the dark energy budget. As the population of black holes grows through mergers and accretion, their cumulative effect might synchronize with the universe entering its accelerated phase over the last several billion years. However, the exact mechanism remains unclear, as constraints from the cosmic microwave background and large-scale structures impose strict limits on the nature of dark energy. Competing theories, such as modified gravity or fifth force fields, continue to challenge this idea, and future observations of black hole distributions may finally provide the clues we need. An even more profound perspective suggests that our entire observable universe might actually be the interior of a black hole residing within a much larger parent universe. In this scenario, our Big Bang corresponds to the moment a singularity was generated during a collapse in that parent realm, and the expansion we see today is the internal stretching of that black hole's own space-time. Its event horizon would lie far beyond our observable limit, making it invisible to us. The compression of space-time, the slowing of time, and the large-scale uniformity of our cosmos all find fascinating parallels in the physics of black hole interiors. If the holographic principle is correct, the horizon of this parent black hole might encode every piece of information within our own universe. In traditional physics, the event horizon is a one-way door. If we are inside, we are completely cut off from the outside. Yet, if every one of the trillions of black holes in every universe allows for the birth of a new cosmos, an endless branching tree of realities emerges. The physical constants in these different universes could vary wildly, some with gravity so strong that stars collapse instantly, others so weak that galaxies never form. Perhaps some have a different speed of light or a completely foreign flow of time, meaning universes capable of nurturing complexity and life may represent only a few rare branches on this magnificent tree of existence. If black holes truly are gateways to new universes, the question remains whether we could ever travel through them. The extreme conditions near the event horizon would likely destroy any traveler, and the breakdown of space-time at the center makes navigation seemingly impossible. Nevertheless, the concept of a black hole multiverse remains a compelling answer to fundamental questions about our origins and the nature of the Big Bang. Each universe is simultaneously a product of the past and a seed for the future. That concludes our journey into the depths of the cosmos for today. I hope these thoughts accompany you into a wonderful dream and a beautiful day ahead. I will see you in our next episode.